Hey, welcome back to your favorite calculus class. We're going to take a look at related rates. So just a little introduction. We've seen how the chain rule can be used to find the dy dx implicitly, right? So another important use is to find rates of change using this chain rule. So we're going to look at the rate at which some variables change when it's known how the rate of some other variable changes. Okay, so these are called related rates problems. Let's do some implicit differentiation here where we take the where we differentiate both sides of the equation with respect to t. Okay, so if we have the equation y equals x squared plus 3 and we differentiate with respect to t on both sides, then we take the derivative of, notice the variables disagree, so we take the derivative of y, which is 1, chain rule dy dt. Over here we take the derivative of x squared, 2x, again variables disagree here, so we have dx dt, and then of course derivative of 3 is 0, so plus 0. Now notice it says find dy dt, so we have 1 times dy dt is just dy dt. Find dy dt when x is 1, given that dx dt is 2. So we got 2 times 1 times 2, we got 4. So dy dt is 4. So this is, we took the derivative with respect to t, even though the equation is in terms of x and y. So you can do that. That's like taking the, let's do another one here. We're going to do this one orally, and then we'll work out a couple more. So when water is drained out of a conical tank, you can see the water being drained here as the height changes, right, as time goes on. So the volume in this would be pi thirds times r squared h, depending on what the height is at however much time has passed, right? So you can differentiate this with respect to t, both sides. So you have volume equals pi thirds r squared h, and you notice we're taking d dt on both sides, right? So the variables disagree. So you get derivative of v is just 1, dv dt, then you go through and you take that, and you notice, you can see that the rates of change of v, rate of change of the volume is related to the rates of change of both the h and the r, right? So the rate of change of the volume depends on what your radius is. So the rate at which the volume is changing depends on what the radius is at that time, as well as the rate at which the height is changing, as well as the height, as well as the rate at which the radius is changing. Okay, and that's the rate at which the volume is changing. Okay, let's do an example here. We got a pebble dropped into a calm pond, causing ripples in the form of concentric circles. Okay, so we've got this pebbles dropped in, right? It hits, and then it ripples out, right? And as time goes on, circles get bigger and bigger and bigger, right? So the radius r of the outer ripple is increasing. Well, first of all, area of a circle, right? So what's our given equation? We say, well, we know the area of a circle is pi r squared, right? Now, let's continue on here. Second sentence. The radius r of the outer ripple is increasing at a rate of a foot per second. So what they're giving you is they're giving you the rate of change of the radius. They're giving you the rate of change of the radius. So they're giving, so given is the rate of change of the radius, dr dt. So that's a foot per second. Okay. Now, when the radius is 4 feet, at what rate, so when the radius is 4 feet, at what rate is the total area of the water, of the disturbed water changing? So in other words, what's the rate of change of the area? At the time, oh, I'm sorry, that's a question mark there. Question mark. What's the rate of change of the area at the moment, right when the radius is 4 feet, at that moment, what's the rate of change of the area of the disturbed water changing at that moment? Okay, so we're going to take our area formula. Area is pi r squared. We're going to take the derivative with respect to time on both sides. So d dt. So we'll take this derivative, differentiate implicitly. So derivative of a is 1 dA dt. Over here we got 2 pi r dr dt. And we want to know, what's our dA dt? When our radius is 4 feet and our dr dt is 1 foot per second. That's the rate at which the radius is changing. So we got 8 pi square feet per second. Let's say, punch that in. 25.133 square feet per second. That's how fast the rate of change of the area. Okay. Let's do another one. Air is being pumped into a spherical balloon at a rate of, so this is the rate of change of the volume. So we're given dV dt is 4.5 cubic feet per minute. Okay. Find the rate of change of the radius. So what's rate of change of the radius? Rate of change, again, that's the derivative. Rate of change. What's the rate of change of the radius? When the radius is 2 feet. When the radius, so how fast is the radius changing? When the radius, at the moment that the radius is 2 feet, right at that moment, right? Because this air is being pumped into it. It's being pumped into this balloon at 4.5 cubic feet per minute. Okay. So again, we've got the formula. We got to have that formula. So what's the formula you're working with? Take the derivative with respect to time on both sides, d dt. So we got 1 dv dt. Over here, this is the constant. 4/3 pi is our constant. And then we take the derivative of r cubed, 3r squared. Don't forget dr dt on that. So dv dt, 3's cancel, is 4 pi r squared dr dt. And we know dV dt, the rate of change of the volume, is 4.5 cubic feet per minute. 4 pi, our radius is 2 feet, so 2 feet squared. And we're solving for dr dt. Okay, so we divide both sides. Well, we got 4.5 cubic feet per minute equals 16 pi square feet times dr dt. Divide both sides by 16 pi square feet. 16 pi square feet. And dr dt is 0.0895. This will be in feet per minute, right? Feet. Changing your radius here. Feet, t, dt units for time in a minute, right? 0.0895 is the rate at which the radius is changing, okay? So when you're solving related rate problems or just story problems in general, I always like to think about the acronym GUESS. What are the givens that you have? What are your unknowns? What's the equation involved for this concept you're working with? And then you're probably going to be substituting and solving. In our case, we're doing a little bit of implicit differentiation, right? So we're using the chain rule and so on. Here's how your authors put it out there similarly. The problem solving with related rates, this table is just giving you a verbal statement, right? So the velocity of a car after traveling for 1 hour is 50 miles per hour, right? 50 miles per hour, so that's the rate of change. dx dt, the distance traveled there, right? T equals 1. Water is being pumped in a swimming pool at a rate of 10 cubic meters per hour, right? Volume, so the volume's changing, and so on, right? So it's giving you the rate of change, right? So read it very carefully. Those are verbal statements showing you how they're explaining the rate of change there. Thank you so much for listening. We'll see you guys next time.